Hello students, this is a video with examples from section 8.4, which are looking at some of the polar graphs and then also looking at changing between rectangular and polar equations. You can graph some of these in Desmos as well. I posted a video on Canvas that shows you how to change the settings so that you get this polar grid that's circular. Just some of the basics is that when we have a number that is given in polar form, it's listed as the first number being a radius. Oops. A radius, how far out we're going to go from the origin, and then the angle is given second. So if we were given, for example, the point 4, pi, then we would go to where the angle is pi. I guess that one should be over here on the other grid. I put one in degrees and one in radians. So 4, pi would be on this grid at pi, and I would go out 1, 2, 3, 4 rings. So it would be this point here. It's going out 4 spaces from the origin. If I were to graph, let's say, just r equals, let's say 3, that means that everywhere the radius is going to be 3, and so that would be a circle that's out at the third ring going all the way around, so the radius of 3 completely around. If I were to graph, let's say something like theta equals pi over 3, that's going to be a line that's going through the origin at pi over 3. This will be in the positive direction because it's going towards the angle. And then if I go in the opposite way, this is going to be going in the negative direction, away from the angle that was given, which is pi over 3. The reason I bring that up is because if I were to say, going back to the side that has the degrees, if I were to graph, let's say the point -3, 135 degrees, I go to where 135 degrees is over here, but then from the origin, I'm not going to go toward the angle, I'm going to go in the negative direction away from that angle. So I'm going to actually go out this direction. And I'm going to go until I'm at 3 places out, 3 rings out. So that point is going to be here. Kind of hard to see on this. 1, 2, 3, right here is going to be the point, -3, 135 degrees. I'll just do one more. What if I were to graph, let's say 3, -315 degrees. So I'm going to go in the negative direction of 315 degrees, which is going to be swinging all the way around to 45, right? Because I'm going from 0 this direction, negative. And I'm going to go towards that angle, towards the angle where I've drawn the star, 3. I'll go out 3 rings, so that's going to be there. All right, so that's just some of the basic graphing. More of what we're going to be doing is changing between polar and rectangular coordinates, and then changing between the equations. So some of the basic information that we need is just to kind of remember how we're going to change between them. If I have an angle theta, this side of the triangle would be the x-coordinate, this side is the y-coordinate, and then the hypotenuse would be r, or the radius of a particular circle. And the point that's out here can either be denoted with the coordinates x, y, which would be rectangular. That's how we're used to graphing. Or instead, I could have it denoted as r, theta, and that's the polar version, where it's talking about how wide the angle is open for that triangle and what the length of that radius is going to be. So we'll use those. And then there's some relationships that come up as a result. So some of the relationships are we talked about this in the last section, that the length of the radius, or the absolute value, is the square root of x squared plus y squared. We know that the cosine of theta is x over r, and we'll actually use that in this format. We'll use it rearranged as x equals r cosine theta. We also know that the sine of the angle is y over r, and again we'll rearrange that and write it in a different format as y is equal to r times the sine of theta. And then the last, which is one that we haven't used yet, which is the tangent of the angle is y over x. And we'll use that sometimes if we don't know what the given angle is and we're trying to figure it out. Okay, so let's do some examples of changing into rectangular coordinates. So we're given the point 6, 30 degrees. So this point is at 30 degrees, but out 6 as far as the radius is concerned. So using some of those relationships that we just wrote above, we know that x is the same as r cosine theta, or in this case, x is going to be 6 times the cosine of 30 degrees, or 6 times square root of 3 over 2, which is just 3 times the square root of 3. We can do that same thing to find y. Y is going to be r times the sine of theta, or 6 times the sine of 30 degrees. The sine of 30 degrees is 1/2. So we're getting that y is equal to 3. So the rectangular coordinates for this are going to be 3 times the square root of 3. Oops, that's weird. 3 times the square root of 3, and then 3 for the y coordinate. Well, let's do another one like that. Let's consider the point 1.4, 225 degrees. So x is going to be r cosine theta, or 1.4 times the cosine of 225 degrees, which is 1.4 times negative square root of 2 over 2. If I take the 2 and divide it into the 1.4, that gives me negative 0.7 times the square root of 2. Y is r times the sine of theta, or 1.4 times the sine of 225 degrees, which is 1.4 times 225 is in quadrant 3, also negative root 2 over 2. So I'm getting the same answer here. I'm getting negative 0.7 times the square root of 2. So the rectangular coordinates for this are going to be negative 0.7 square root of 2, negative 0.7 times the square root of 2. All right, let's do a couple examples going in the other direction. Let's change to polar coordinates. So let's start with the point -4, 4. And we need to now find r, and we need to find theta. So we'll use the formula of taking the square root of a squared plus b squared to find r, or -4 squared plus 4 squared, which will end up being 4 times the square root of 2, right? Okay, so that gives us the radius. And then we need to use the angle, we need to find the angle, and so we'll use the fact that the tangent of the angle is y over x. Or in this case, the tangent of the angle is 4 over -4. So we're asking, when is the tangent of an angle equal to -1? And we know that happens in 2 locations, but this particular point is in the the second quadrant, right? So we know that this is going to be at 3 pi over 2. Theta is equal to, 3 pi over 4. So then we know that the polar coordinates for this number are 4 root 2, that's r, and then 3 pi over 4. All right, let's do another example like that. Let's consider the point -square root of 3, 1, and let's change to polar coordinates. R is going to be -square root of 3 squared plus 1 squared. That's going to be square root of 4. This is going to be 2. And then tangent is y over x. So 1 over -square root of 3. Let's see what happens if we plug this into the calculator. If you plug into the calculator tan inverse 1 over -square root 3, the calculator gives you back -30 degrees. So the calculator tells us that the answer is over here at -30 degrees. But given the coordinates, we know that this should be in quadrant 2, right? So we're going to swing over to the other side over here, and we know that the answer that we're going to be giving is 150 degrees, or 5 pi over 6. So our answer for this problem is going to be 2, that's the radius, and then 5 pi over 6, that's the angle. All right, for the next set of examples, we are going to be converting into polar hang on one second. We're going to convert polar equations, and then we're going to convert into rectangular equations. So we're going to convert to a polar equation. Now, Desmos can sometimes handle the polar equations, but sometimes it can't, and you need to switch it back to a rectangular equation. So for this first example, you are used to seeing things that look like this format: 5x plus 3y equals 4. And we know that this is a linear equation. X and y are both raised to the first power. But when we're in calculus, sometimes we want things to be written in terms of sine and cosine. especially in calculus 2. And so we need to be able to convert this. And so we'll use the relationships that we had before. We're going to use the fact that x is the same as r cosine theta. And we'll also use the fact that y is equal to r sine theta. And so we'll make substitutions. So I'm going to put 5 multiplied by r cosine theta. I'm just plugging that in for x. And then I'll have 3 multiplied by r sine theta. And that equals 4. And then what I'm going to do is factor out an r from both of these out to the front. So we'll have r on the outside, and then we'll have 5 times the cosine of theta plus 3 times the sine of theta equals 4. And that is our polar equation. All right, let's do another one like that. Let's look at x squared plus y squared equals 36. Some of you might know that when you have both x and y squared, that gives you a conic section. And in this case, it ends up being a circle that's centered at the origin, and the radius is 6. It's the square root of 36 there on the other side. We'll actually talk about conic sections in a couple weeks here. We've only got a couple weeks left, but I think in 2 weeks we'll talk about conic sections. So we know that this should end up looking like a circle. Let's make substitution. For r, for x, we'll put r cosine theta, and that's going to be squared. And for y, we'll put r sine theta, and that's also going to be squared, equals 36. I'm going to square the r and the cosine theta, so I'll have r squared cosine squared theta, and then r squared sine squared theta is 36. And then I'm going to factor r squared out to the front. Factor out r squared. And I'll have r squared times cosine squared theta plus sine squared theta equals 36. Now, this is one of our Pythagorean identity, right? This is just equal to 1. Sine squared plus cosine squared is equal to 1. So we end up with r squared is equal to 36. And then if I take the square root of both sides, I get r is equal to 6. When we were talking a few minutes ago about graphing, we said that if we get an equation where it's just giving us the radius, that is a circle out of the 6th rung out from the origin. And so this is the polar equivalent to the rectangular version that we're used to seeing. All right, I've got a couple more examples like this. Let's consider x squared minus 2x plus y squared equals 0. So x is going to be r cosine theta. And y is going to be r sine theta. Okay. So I'm going to take these two and put them together because it's kind of like the problem we were just doing. I'm going to have r squared cosine squared theta plus r squared sine squared theta, and then just leave this minus 2r cosine theta over to the side here. And then just from this part here, I'll factor that r squared out to the front. We'll have r squared times cosine squared theta plus sine squared theta. And so then I can get rid of the cosine squared sine squared because that's just equal to 1. So I'll get that r squared minus 2r cosine theta is equal to 0. And that's our answer for that one. All right, one more of those and then we'll switch to the opposite direction. Let's look at 3x squared y equals 81. So we'll have 3 r cosine theta squared times sine, r sine theta equals 81. So 3 r squared cosine squared theta times r times sine theta equals 81. I'm going to divide both sides by 3 just to kind of simplify this here. So I'll have, combining all the r's together, I have r cubed cosine squared theta sine theta equals 27. And that's my final answer here. All right, let's get a new sheet and do a couple examples going the other direction. For these examples, we're going to convert to a rectangular equation. Most of the time, if you're trying to get an understanding of what the graph looks like in Desmos, you might want to convert it to a rectangular because that's what Desmos is used to it having as an input value. So for our first example, let's look at r equals 5. Well, we've been talking about this equation, and we know that this is a circle with a radius of 5. But we know that r is equal to the square root of x squared plus y squared. So I'll put x squared plus y squared, square root is equal to 5. And then if I square both sides to get rid of that square root, I have x squared plus y squared equals 25. This is the version that we're used to seeing for conic sections, a circle centered at the origin with a radius of 5. All right, what about this example? Theta equals 3 pi over 4. We know that if we have a polar graph, that this graph should be at the angle 3 pi over 4, which is here, and it should be going towards that angle and away from that angle. It should be a straight line like this. And so that's what it looks like on a polar graph, but we want to have the equivalent version in the rectangular equation. So we're going to use what we've been given regarding tangent. We know that tangent of an angle is y over x. And we're given the angle here. We're given that the angle is 3 pi over 4. So let's write tangent of 3 pi over 4 equals y over x. We can plug tangent 3 pi over 4 into the calculator, or we know that value from the unit circle. We know that that's just -1. And then if we multiply both sides of this by x to clear the denominators, we're going to get that -x is equal to y. Or you're probably more used to seeing this as y equals -x. That's exactly the graph that we've drawn there. We have a straight line, goes through the origin with a slope of -1. So this is the rectangular version that we're used to seeing. All right, a couple more examples like this, ones that are a little more complicated. Let's look at r plus r cosine theta equals 3. What could this graph possibly look like? Well, if we make the exchange for r, R is the square root of x squared plus y squared. R cosine theta, this is equal to x. Because I have a square root, I want to try to get rid of it. And to do that, I need to move everything away from the square root so I can square both sides. So I'm going to subtract x from both sides. And then I'll have the square root of x squared plus y squared is equal to 3 minus x. Now I can square both sides. When I square the left side, I'll just have x squared plus y squared. And on the right side, we'll square the first term. We'll multiply the two terms together and double, so that'll be minus 6x. And then we'll square the last term. All right. It looks like I've got an x squared on both sides, so those are going to go away. And I have y squared equals 9 minus 6x, or y squared equals negative 6x plus 9. So that's something that we could plug into Desmos and get a graph for. All right, one final example for today. Let's look at r equals 2 over 1 minus the sine of theta. I don't like how this looks with the fraction. So I think I'm going to start by multiplying both sides by 1 minus sine theta, just to get rid of that fraction. And then I'm going to distribute the r to both of these items here. So I'll have r minus r sine theta equals 2. What I'm trying to do is rearrange it so that I can get r times sine or r times cosine, because I know how to make those substitutions, right? I know that r sine theta is the same as y. So now I can rewrite this as r minus y equals 2. I know that I'm done when I don't have any angles left, and I also don't have any r's left. I want to have only x's and y's to be my final product. So I'm going to move the y to the other side. You'll see why in just a second. It's kind of a trick that you learn. So r is equal to y plus 2. Because now what I can do is square both sides. Rather than making an exchange. Now I'm going to square both sides because I know that r squared is equal to x squared plus y squared, right? So I'll have r squared is equal to y squared plus 4y plus 4, or x squared plus y squared equals this whole thing. I have y squareds on both sides, so they're going to cancel each other out here. And I'll be left with x squared equals 4y plus 4. So I've only got x's and y's in my final equation, so I know that I'm done. All right, thank you for watching. And if you have questions, send me an email or send me a message through Canvas. Have a good night.